would be what? 1, 4, 9. See the difference between those two? This one we assume starts at 1. This one someone told us it starts at 3. How about this? Stop at 7. So this would be what sequence? 25, 36, 49. We're going to do n squared. We're going to start at 5. We're going to stop at 7. So that's 5 squared, 6 squared, 7 squared. Done. All right. No questions yet? Now, as we proceed through this chapter, there are some sequences that come up a lot. And we need to know how to generate these sequences on our own. So common sequences. Here we go. What if I want to create the sequence of natural numbers? My question to you is, what is the definition here of A sub n? What A sub n will generate that sequence of numbers? What do I need to define it to be? A sub n needs to be equal to what? N plus 1? What would n plus 1? Remember, we're going to start at 1, right? So if I plug 1 into this, I'll actually start at 2. And I don't want to start 2, right? I want to start at 1. So just n? That's it, right? If you define A sub n to be equal to n, you will generate the list of counting numbers, right? And we should always be able to generate that list. That's trivial almost, yeah? I'm getting a lot of looks like people are tired or... Look, you've got to pay attention. You've got to be ready for this, because if you're half awake in here right now, you're going to get blown out of here in a little while, all right? You need to like snap up, go outside, go up the stairs and down the stairs a couple of times, whatever. You got to get up, you got to be ready, all right? Because this is where I start to see a lot of people will fall off, okay? They look at this and they just don't see it. It's because they're half awake. All right, how about this? So did anyone have a problem generating that sequence right there, up there? No one? Everyone understood the formula? Okay. This one doesn't come up as often as this one does, but there's something in this that I want you to recognize. Anyone see it? It's this sequence, right? Except everything's been shifted. So like they keep going up by 1, which is what this one does, right? It's just they start at a different place, don't they? Instead of starting at 1, I start at -2. And instead of 2, I'm at -1. And instead of 3. So each of these is 3 behind that one up there, isn't it? So why don't we just use that sequence and take 3 away? A sub n equals n minus 3. We're done. Do y'all see it? Okay, who said that? Someone said n minus 3. Who said? You're out. You're no longer, you can't answer any of the others yet. All right? Should have what? Okay, I'll let y'all have one more shot. Then after that, whoever says it, all right? How about this one? 2, 4, 6. 2n? 2n. Yeah, y'all see it? It's just, those are all even numbers. Yeah, try 2 times 1, 2n. 2 times 1 would be 2, and then 2 times 2 would be 4, and then 6, and then 8. Y'all see it? Now these are the even numbers. All right, so put a little star next to that. That's how you generate the even numbers, 2n. I know this kind of still seems a little bit like, okay, where is it going to get hard? Just bear with me. Doesn't have to be hard, just, how about this? -8, -6, -4, -2, 0. All right, so who said 2n? You're out. Get out. No, I mean you're out. What is this? Yeah, go ahead. 2n minus 10. So you're seeing it's the even numbers. You're just shifting everything back 10, right? Yes? So 2n a sub n equals 2n minus 10. And you can always check it by just plugging 1 in first. If you plug in 1, you should get -8. You plug in 2. 2 times 2 is 4, minus 10 is -6. But see, it's more important to see it that way. Even numbers, moving everything over by 10. You've got this down. Y'all are ready. One, 3, 5, 7, 9. Okay, if you've answered, you can't answer. Can't answer, Ron. Say what? Okay. Anyone? 2n minus 1? So how are you seeing that? I'm just curious. I'm just trying to figure out what you're thinking.
Well, I just plugged in 1 and then subtracted 1.
But where did you get the formula 2n minus 1 from?
I just plugged it in.
And this is what's hard about this now, okay? It's because I can't teach someone how to see that. And that's how the rest of this chapter is going to go. I can't teach you to see something that you either see or don't see. Right? Now, I can try and give you some more of a systematic approach. Isn't this all the even numbers minus 1? Isn't 1 2 minus 1? And isn't 3 4 minus 1? And isn't 5 6 minus 1? So aren't all the odds just the evens shifted over 1? So that's one way you could kind of visualize it, maybe. 2n minus 1, right? Okay. What about this? (2n plus 1). That's all the even numbers again, but this time shifted the other way. Instead of 2, it's 3. Instead of 4, it's 5. Instead of 6, it's 7. So it's up by 1 instead of down by 1. So 2n plus 1. Okay, we're getting fewer and people can answer now. That's kind of bad because the harder ones you're going to leave. Very important one right here. How are you going to generate that? If you answered, you're out. Anybody? You're getting there, getting warm. 1 to anything should be itself, should be 1, right? 1 raised to any power should be 1, so you can't use 1. There you go. Did you say negative the first time? I didn't hear negative. You said 1. Negative 1, that whole thing to the n. Does that work? So if you plug in 1, you get negative 1 to the first power, which would be just itself. If you plug in 2 for n, you get negative 1 squared. Negative 1 times negative 1, positive 1. Negative 1, now you plug in 3, right? You get negative 1. Every even power is going to be positive. Every odd power is going to be negative. And so this will generate this, won't it? This is a very standard sequence. We call this an alternating sequence. You see why? Alternate signs. So this is the first example of an alternating sequence. Just out of curiosity, would this have worked? Yes? Yes, because what would happen if I plugged in 1 is that I would start with what? 3, and that would still be starting a negative, right? And then the next number would be what? After 3 would be 4. That's even. And then 5. So I could have done that, or I could have done, well, could I have done this? Would that have worked also? In fact, n plus what? Any even would have worked, right? N plus any even number, and I would have still generated that same sequence. Just wanted to point that out. Now, what about this one? 1, negative 1, 1, negative 1. Negative 1 to the n plus 1. Will that work? If you plug 1 in here, what do you start with? 2, and that's going to give you a positive 1. I've got to sneeze. Excuse me. Try to cover the mic there. Yeah, so that should work. If you plug in 1, you get negative 1 to the 2. Which would be 1. And then from there on out, it would be alternating, wouldn't it? You could do any odd number up there, couldn't you? N plus any odd number, and it would still work. As long as n starts with what? 1. All right. Last one. Okay. This looks good. Okay. This is more like the stuff we need to be able to handle right here. Because that looks pretty complicated. You can start going, okay, 2/5 and negative 4/25, and start to try and find like some relationship between that number and that number. The way I like to look at these is just break it all apart. Okay, first, it's an alternating sequence, right? It starts positive, then negative, then positive, and I'm assuming negative, right? How do I create an alternating sequence that starts with positive 1, with a positive number? Negative 1 to the n or n plus 1. Does everyone agree that that will start me with a positive? And on the next one, I would get a negative, and then positive, and then negative. So that should create the sign change I need, shouldn't it? Now let's look at the fraction. What's happening in the numerator? 2, 4, 6, 8. So the numerator are just the even numbers, right? Starting at 2. So 2n up there. The denominator, hold on. Ron, come on.
Yeah, 2 and then the bottom is 5 then.
5 to the n. To the n? Or 5n?
To the end.
To the n. So 5 raised to the n. They're all powers of 5 down there, aren't they? 5 to the first power, 5 squared, 5 cubed. And so that takes care of everything, right? That should create the alternating we need. The numerator should come out right. The denominator should come out. You could do certain things to this, like you could move this up here, but that's it. I mean, that formula will generate that sequence. Now, the formula for a sequence is not unique. Someone could probably come up with another formula that's just this tweaked up a little bit, and we would get the same sequence. So don't ever believe that, your answer has to match the back of the book all the time, because you can be off a little bit. I mean, as long as you can simplify yours into theirs or theirs into yours, then you're good. Always just check it. Plug in one, make sure you get the first one. Plug in two, make sure you get the next one, so on and so forth. All right, now every sequence I've shown you so far, either I've given you the definition and we wrote out the sequence, or I gave you the sequence and you came up with a definition. There are some other types of sequences out there called recursive sequences. And there's a very famous one that you may be familiar with. I'll write it out first. Or maybe a little more. Anybody recognize that sequence? The Fibonacci sequence. Fibonacci, named after an Italian mathematician. So what is the pattern in the Fibonacci sequence? 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. So how do I get the next guy out here? What do? I add up the previous two. Right? How did I get 21? I added 13 to 8. How did I get 13? I added 8 and 5. How did I get 8? 5 and 3. So the next number out there should be what? 30 what? 4? That's the Fibonacci sequence. The thing about the Fibonacci sequence is there is not an easy formula for it. There's not an easy one. But there is a way that you can do it using what's called the recursive definition. And here's how it goes. What we know is that the first guy in the sequence has to be 1. We also know the second guy, oh, that's a girl, sorry. The guy is 1, the girl is 1 also. Okay, the second, I'm trying to be, politically correct here. The first two are 1, right? After that, do you need anything else? You just need to know what to do with those, right? What do you do with those? To get the third one, you add those up. To get the fourth one, you add the previous 2 up. To get the fifth one, previous 2, right? So what I know is this. If I want to figure out the nth one, all I have to do is take what? The 1 in front of that, which would be n minus 1, and add it to the one before that one, which would be what? A sub n minus 2. And that I would do for any n greater than or equal to 3. See if that makes sense to you. So I define the first two. right? Here they are, 1 and 1. Now, every one after that is the sum of the previous two. So if you want to know what the nth one is, you add the n minus 1 one to the n minus 2 one. So if you look at these, it's a little easier if you look at these like maybe these are dominoes. Here are my dominoes. If I'm trying to figure out, whoa, that domino's all messed up. If I'm trying to figure out what the a to the n domino is, right? I have to look at the one before it and the one before that and add those two together. This is an minus 2, this is an minus 1. Take these two and add them up, and that will give me that third one, right? So this is a general formula, but it only works when you're looking at the third domino and out, because the first two are already defined, aren't they? That's what we call a recursive definition, a recursive sequence. Fibonacci's sequence is when these are 1 and this is defined this way. If you change this to a 3, it's no longer Fibonacci sequence. If you change this to a 4 and left this back here as a 1, it's no longer Fibonacci sequence. Fibonacci sequence is a specific example of a recursive definition. It's not the only one out there, it's just a specific one. Yes?
So if you plug in 3 for both ends on your a sub ends?
And like 3 here for your first ones?
Over there, yes.
If you plug in 3
Yes.
right here,
Or, yeah.
then this would become, well, let's do it. A sub 3 would be A sub 3 minus 1, 2 plus A sub 3 minus 2, 1. So the third domino is equal to the sum of the previous two. So, yeah? Okay. I'm not sure if you had a question. Was that a question or?
It's just making sure that that works.
Yes. But see, 2 wouldn't work, right?
Because you would go back to
You would go back too far. You don't know what A sub 0 is because it was never defined. Now there's some really interesting properties of the Fibonacci numbers, the golden spiral and all that stuff, and I could draw it on the board, but you can also use YouTube also to look up things like that. So if you're interested in the Fibonacci numbers, go look it up. All right, now there's one more thing I'll talk about today in the last few minutes, and that'll set us up for next class to get into the heavier stuff. This thing. What is that? Y'all seen that before? N, damn it. Right? And factorial. This is what we call the factorial. And the factorial is just a very short way of writing something out that could be very hard to write out. If you write down 5 with an exclamation point, you mean 5 times 4 times 3 times 2 times 1. You don't need the 1 there, but I just put it for illustration. All it is you take the integer 5 and you multiply it times the next number down, 4 times the next number down, 3 times the next number down, 2, then times 1. And whatever that number is. What is that number? 120? And that is the definition of factorial. Now, written in a more general sense, if you write down n factorial, then it should be n times what? 1 less than that, right? So couldn't I write that like this? N minus 1 times, and then 1 less than that one, which I could write as what? N minus 2. And I keep doing that, dot, 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 until I get to where? How about just 1? How about just 1? When we get to 1, we stop, right? That's the definition of n factorial for n element of, I can't use natural numbers though. What's the double struct z? Uh-oh. So double struct r is all the real numbers. We are familiar with that. Double struct n was the natural numbers, 1, 2, 3, 4, 5, 6. Z, double struct z, are the integers. That's 1, 2, 3, 4, 5 forever, it's negative 1, 2, 3, 4, 5 forever and 0. Right? So this is 0, 1, negative 1, 2, negative 2, both directions forever. No fractions. If you want the fractions, double struck Q. Now that's even more, but it's not everything. Double struck Q is not double struck R, because there are things that are in R that are not in Q, like pi, like the square root of 2. So this is all the fractions. If you put the fractions and the irrational numbers together, you get R. What about what? That's not, oh, what is it?
No, like where would it fall?
You know what? I don't know. I think it's irrational, but I could be wrong. Because it's the golden ratio, right? The golden ratio is not a fraction. If it was, everyone would know what it was. It's something that gets approached in a limit. We never get there, so I'm pretty sure it's irrational. So it would be in here, but not in here. I'll double check that, and I'll let you know. So what am I saying here? N factorial is this, as long as what? N comes from the integers that are greater than or equal to 0. That means these guys over here. So it's the natural numbers, isn't it? It's the natural numbers, but 0 also, right? So that means I can actually find out what 1 factorial is. Yes? What's 1 factorial? 1, okay. 2 factorial, 2 times 1. 3 factorial, 3 times 2 times 1. But according to this, I can also do what? 0 factorial. And so what is 0 factorial? It's 1. Why? We define 0 factorial to be 1. There's a video that you can watch on YouTube. The channel, I believe, is called Number File. I think I showed you with the encryption thing in the very beginning of class. Remember that encryption thing, the very beginning? We didn't do the encryption thing? No? Okay, I thought we did. Number File is a really cool channel if you like numbers. And math, and computer science. Number File. And they have a video on trying to explain why 0 factorial is 1. But for us, we're just going to take it on, we're just going to believe it. It's the definition of 0 factorial is 1. I don't think I have enough time to get into some of the properties of this. Would it make any sense to try and do this? 1/2 factorial. According to the definition, I shouldn't be able to. But there is, and it's a more complicated function we're not going to get into. Number File, they do talk about that, so they get into it pretty deep. What's your homework? Have fun. Have a good Halloween. I do want you to do that surface area homework. There's 3 problems. Make sure you're caught up on the arc length stuff. From the looks of the quizzes, then work on this volumes. You know, make sure you go back and touch on that. Yes? Okay. You're free to go. I'm just going to put this on video. You're not going to hurt my feelings if you leave. This is the Fibonacci golden spiral. So that's a square that has length 1, length 1. So that 1 is not the area, it's the measurement of each side. Remember the Fibonacci numbers are this. So if I draw another square next to this, it also has length 1. Because this side is the same, so it's 1 by 1. If I draw this square, that would be 2 and 2, so this would be 2. And then if I draw this square, it's 2 and 1, so this would be a 3. If I draw this square, this would be 3 and 1, so that's 5. If I draw this square, ooh, that'd be 5 and 1 and 2, that'd be 8. This square would be 8 and 2 and 3, so that would be 13. And then I'm going to go off the board. So if you start out in the first square, the first corner here, and you connect an arc swinging to the opposite corner, and then from that to the opposite corner, 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 you create the golden spiral. And that's the thing that they talk all about, golden spiral. Yeah. That's supposed to appear in nature all over the place and things like that. I've heard different things. I've heard stories supporting that and stories that say it's not true, but either way, that's the golden spiral.